Hello, welcome to the fourth lecture of Naughty Mojo Jojo lectures. Today we'll be dealing with the same topics we dealt with before, but we'll be doing a problem, a different kind of a problem, a bit more complicated one. And first of all, I needed to make something clear. In one of the previous lectures, I told you about atmospheric pressure, right? And I told you 1 atm was the pressure experienced at sea level, right? Was the pressure experienced at sea level. Yes, 1 atm is the pressure experienced at the sea level, but this is not actually same for the case of every countries, because every countries will have different sea levels. Different countries will have different sea levels, and approximately 1 atmospheric and correct 1 atmospheric pressure or 1 atm is seen somewhere in France, I think so. Or I don't think it will vary much in different countries, so I just wanted to make that point clear. You don't want to say that you don't want to. Okay, now moving on to the problem. We consider this shape, this awkward structure, and this is a test tube inverted in a bowl, and let this be mercury. Mercury, Hg. It's a silver color, so let it be mercury. Okay, this is actually a question. Now I'll write the question down. Okay, the specific gravity of mercury is 13.6. Specific gravity of mercury is 13.6. Find the height of the liquid rise in the test tube. Now that is a question. It might seem very hard because you have only one value, specific gravity, and specific gravity, that's a value, or that's a thing you haven't heard before. For those people who understand from my lectures, I don't think they have heard of specific gravity. Now what is this specific gravity? Specific gravity, let me write it down. I'll write it in letters. Specific gravity equal to, I'll do it in another one because let us say it's a formula, is the density of the substance of which the specific gravity we want, divided by the density of water, right? Specific gravity is the density of the substance divided by density of water. You just relate it with the refractive index or something. If you know refractive index, it's kind of easy. Refractive index is the speed of light in vacuum divided by the speed of light in that substance. Okay, you can kind of relate it to that. Okay, now that is what specific gravity is. Now let's do the problem. Okay, let's consider that I'll do it in another color. Let the density of the substance, that is mercury, be X. And what is the density of water? I told it before. The density of water is 1000 kilogram. Sorry, do that again. Per meter cube. Right? Let's make a cube. I'll do it again. Sorry for that. Okay, what is the specific gravity of Mercury? It's given here as 13.6, right? 13.6. So this is 13.6. 13.6, right? 13.6. So now we can calculate X, right? The density of Mercury. What is X? Which is 13.6 into 1000. Let's straight away write it down. 13600. Now what is the unit? It's kilogram per meter cube, right? Okay. Now that is the density of Mercury. Now what is the question? The question is height. Okay, height of the liquid rice. Liquid rice is actually in brackets, in inverted commas. Liquid rice in the test tube. Now what is the liquid rice in the test tube when we consider the figure? I'll do it in another color. This is the liquid rice, right? This much. It's the liquid rice. So let's put it as H. Now when we consider this figure, I had to tell that before, when we consider this figure, this area we consider it as vacuum. Vacuum, right? This area we consider it as vacuum. But this area has air pressure over here, right? If we keep something in air, we'll have air pressure or ATM. This side also will experience the same. Now consider that we have placed this Mercury at sea level in France. What will be the atmospheric pressure experienced over here and here? What is it? Yes, it's over here. 180 m, right? 180 m. 180 m. Okay, that might have sound awkward. Okay, that's the pressure. Now I need some space. Let me remove something. Okay, remove this one. We don't want this. No, we don't want this. Right. We don't want this arrow either. Not that. Okay, is that enough? No, that's not enough. I'll just move this. Yes. I'll just move this one to over here. That was. I'll move this also. I'm keeping this just so you remember it. Specific gravity is something important. Okay, back to our problem. Now, what is pressure? We have an equation for pressure, right? We dealt it with in the last lecture. H rho G. Pressure is H rho G. Now, no, we don't straight away write like that. Okay, what is the pressure over here? The pressure experienced is 1 atm, right? If you write pressure as 1, it's going to be a blunder, because the SI unit of pressure is Pascal. Now, how much Pascal is 1 atmospheric pressure? I've told it before. It's 103,000. 103,000 pascals or Newton per meter square is equal to H. We don't have H, right? We don't have the liquid rice over here. Now, what is rho? The density. We'll calculate the density. Oops. Don't have space. Oh my god. That's stupid of me. Better. H into density into the gravitational constant into 9.8. Now we need to find H, right? H is equal to 103,000 divided by 13600, 13,600 into the gravitational constant 9.8. 0.8. Right? Okay. Now I'll change my color first of all. I need a calculator over here. Oops, sorry, wrong tool. I need a calculator over here. How to do it here? Okay. What is the thing we want? 103,000 divided by 13600 divided by 9.8 is equal to 0.7728. 0.7728. What is the unit? We've done everything in SI unit, so it will be the SI unit. It is meters. Now that is the answer. Oops, I always do that. Sorry. Now that is the answer to this awesome question. So I hope you'll watch our next video. Like always, thank you for watching.